Let's get radioactive and talk about radiometric dating. Radioactive dating is a form of numerical dating, where age is given in a number of years, or millions of years, or billions of years. This is in contrast to relative dating, where you determine that one event is younger than or older than some other event in geologic history. Radiometric dating is a recent development, only available since about 1900 and only common since about the 1950s. We should also point out that since the 1985 North American Code of Stratigraphic Nomenclature, the term absolute dating is not supposed to be used anymore for numerical dating. Originally, absolute was in contrast to relative, but the word absolute in English has another connotation of being more true than something else, and that is not the case here. Numerical dates are no better than or worse than relative ages. The basic principles of radioactive dating is fairly straightforward. Certain elements in the periodic table are naturally radioactive and break apart spontaneously to form particles, energy, and give off radiation. That energy is usually in the form of heat, and the heat from radioactive decay is what powers the Earth's interior and keeps it molten. Three sets of particles are given off by the radioactive decay. Alpha decay produces a helium nucleus. Beta decay produces an electron. Gamma decay produces high-energy gamma radiation. The reaction occurs when a radioactive or unstable parent isotope breaks apart spontaneously, undergoes decay, and produces a non-radioactive stable daughter isotope. The process is measured in what is called a mass spectrometer, which measures different isotopes at different masses by running them through an electric field and a magnet, where the heavier isotopes are deflected less than the light isotopes. Some isotopic decay series are very simple, but others go through multiple stages of different isotopes, some of which are long-lived, some of which are short-lived, before they finally reach a stable final daughter product. Typically, when we want to measure time with something changing, we think of linear decay, where a candle might burn a certain number of inches per hour. Or we might think of an hourglass, where a certain number of grains of sand percolate through the neck in a certain amount of time. But radioactive decay does not work like that. Instead, it decays at a different rate depending upon where we are in the decay series, with decay going faster at the beginning and slowing down toward the end. This is called exponential or logarithmic decay, because the formula for that curve is a logarithm or exponent. Another way of thinking about it is to talk about what are known as half-lives, the amount of time necessary for half the original parent material to decay to the daughter product. For example, if we have a crystal which locks in a certain number of unstable parent atoms at the beginning at time 0, in one half-life, half of those red stars will have turned to green stars, and then half again will have turned to green stars in 2 half-lives, and 3 half-lives you have just a few red stars of the parent atom. In other words, decay is very fast in the first half-life as there are lots of unstable parent atoms, but it slows down through time as there are fewer and fewer parent atoms and mostly stable daughter atoms. The oldest system to be developed back in around 1911 is the uranium-lead system, where uranium-238 decays to lead-206 and uranium-235 decays to lead-207. Both of these decay series go through numerous intermediate steps between uranium to thorium to lead. As with all the other series, at the beginning it's entirely uranium. After one half-life, it's half and half uranium and lead. After 2 half-lives, it's 25% uranium and 75% lead. And after 3 half-lives, it's 12.5% uranium and the rest is lead. Both of the 2 uranium-lead series have very long half-lives in the billions of years, so they're only used for very old rocks, at least 1 billion years old or older. Likewise, the rubidium-strontium system has a half-life of 47 billion years, so it's only useful for rocks that are 1 billion years old and older. For most geological problems, the most important system is potassium-argon. Although it has a 1 billion-year-old half-life, potassium is a very common element in many common minerals, such as potassium feldspar and certain micas. So even with a very, very slow decay rate, there's a lot of parent material, and you'll get a measurable amount of daughter in a relatively short period of time. Like the other systems, unstable potassium-40 decays to argon-40. The decay process is rather complicated with both beta decay and electron capture involved. The main thing to remember about potassium-argon, uranium-lead, and rubidium-strontium is it only works in an igneous rock where it crystallizes out of a melt. As the melt cools down, crystals form and lock in the parent atoms. Once those crystals are formed, the system is locked in. After it's locked in, the decay is then trapped in the crystal lattice. This distinction is important. These kinds of systems only work on igneous rocks and not on sedimentary rocks, so you cannot date sedimentary rocks directly. You also have to have the freshest, most uncontaminated crystals to avoid leakage of parent or daughter atoms, or also parent or daughter atoms coming in from the outside. And finally, we must remember that this is an estimate with a plus or minus error bar inherent in the way these machines are run. If you do not see the error bar, it's not trustworthy. If an age is quoted at 100 plus or minus 5 million years, it actually means that there's a 95% probability the true age lies somewhere between 95 and 105 million years. Since we can't use radioactive dating on sedimentary rocks, we need to use their relative age, such as Miocene or Oligocene, interbedded with lava flows or ash falls to get a precise numerical date. If we don't have interbedded lava flows or ash falls, the next best method is an intruded dike, which gives us a younger age of the beds. If we don't have that, then a dike which intrudes the older beds is cut by an unconformity and then is covered by younger beds gives us at least one bracket. For example, in this particular cartoon, the granite of 125 million years old tells us the Cretaceous is younger than 125, but older than the 80 million year old dike which cuts through it. Above the 80 million year old dike is a Paleocene sand, so the Paleocene must be younger than 80, but older than the volcanic ash lying above it, which is dated at 50 million years old. This is the way we bracket the sedimentary rocks and their fossils and get their numerical ages. Many people have heard about carbon dating, or radiocarbon dating, or carbon-14 dating, which is the most familiar method. This method works when the nitrogen-14 in the atmosphere is bombarded by solar energy and turned to carbon-14, which then is incorporated into the tissues of animals and plants and begins its decay once the animal or plant dies and no longer exchanges carbon with the atmosphere. Unlike the previous methods we discussed before, you can actually directly date objects using carbon-14. It works on shells, on bone, on wood, and on many other carbon-based tissues. The sample of carbon-rich material is burned in a vacuum furnace, and the carbon is released to measure in the mass spectrometer. But the method depends on how fast the decay occurs. Uranium, lead, and rubidium strontium work on billion-year-old rocks. Potassium argon for most geologic settings are from over 1 million years old. But carbon-14 has a very short half-life, just over 5,000 years, so it decays very rapidly and mostly only useful for objects less than 60,000 to 80,000 years old. Thus, it's only useful for things less than 80,000 years old, like archaeology uses it, or like working in the last ice age. You would never use it on a dinosaur bone, which is much older than 80,000 years old. Of course, young Earth creationists do not accept anything that's older than 10,000 years old, so they try any method they can, dishonest or otherwise, to try to discredit it. The most common way in which they try to discredit radioactive dating is to claim that something was dated by carbon-14 at 80,000 years old and then by potassium argon at 40 million years old, or something like that. All this demonstrates is that they're incompetent. No geochronologist in their right mind would take radiocarbon on anything older than 80,000 years old, because after that the clock is stopped and the date is no longer useful. Therefore, the only useful date for something like that is the 40 million year old date on the much older fossil. They harp upon examples of failed radiometric dates as if it proves that no date can ever be trusted. But a good geochronologist is always skeptical of their dates and always double-checking and triple-checking to make sure there's no problem. Sure, once in a while, a date is bad, but we always know this because we can triple-check it against other different systems from the same rock. We do not throw out every clock just because one is stopped working. Geochronology is now a well-established science with 100 years behind it, with lots of methods of cross-checking and of validating dates. So if a geochronologist publishes something, it's based on a lot of very careful scientific analysis. Young Earth creationists would love to imagine that no radiometric date can be trusted, but in fact, we have thousands of radiometric dates, and they all give consistent answers when they're carefully analyzed.